All right, hey, welcome to installment 2 of acid-base equilibria. So in this one we're going to discuss the Bronsted-Lowry Model, and typically on the AP exam it's understanding of the Bronsted-Lowry definition of acids and be able to write those kind of chemical equations that is going to be tested on and expected. So pay close attention to how to do this. All right, so and then we're also going to talk about conjugate acid-base pairs and what that means. Okay, so let's switch. I'm going to go with a little pink in this one. So in the Bronsted-Lowry model, it's really quite simple. An acid is simply a proton donor. So anytime a chemical or a species donates a proton, and when we say donates a proton, what we're talking about is a hydrogen ion. So a hydrogen ion essentially is just a single proton. And so a proton donor is an acid, and a proton acceptor is a base. For example, if we take a look at this example right here, we have HCl going into water. And so if we bubble HCl gas into water, here's what happens. The HCl donates a proton to the water molecule, and so then it creates this molecule right here, which we call a hydronium ion. So the hydronium ion, H3O, is also called a hydrated ion. It's received an extra hydrogen. It has had a proton donated to it, and so it becomes H3O. And so this is how you write it. So this would be written correctly in the Bronsted-Lowry model for the idea of an acid. And so similarly, if you were to write it in the Arrhenius model, it would be something like HCl. Actually, you wouldn't even put plus water. It goes in there, breaks up into these two ions, and these are dissociated. This would be a gas, and these, of course, both would be aqueous. So this would be our Arrhenius model, and then this is the Bronsted-Lowry model. All right, let's look at a couple more examples. I'm going to continue to work that in as I go through, and then we're also going to talk about conjugate acid-base pairs and how to identify those. Okay, so when we look at this particular equation right here, we have a little bit different situation. So the carbonate ion goes into water. And notice what the carbonate ion does. The carbonate ion actually takes a proton, or takes a hydrogen ion, which is a proton. So it qualifies under the Bronsted-Lowry model as a base, a proton acceptor. Right. In the case over here, we could have done this. We could have said that the acid is here because that's the proton donor, and then water in this case acts as a base because it's the proton acceptor underneath the Bronsted-Lowry model. So here we are. So the carbonate ion goes into water. It takes one of the protons. It becomes a -1 charge instead of -2, and then you're left with some hydroxide ions. And so this right here is a Bronsted-Lowry base. And then the water in this case acts as an acid because the water donates an electron. So one of the things that we just see is in this model right here, we see water acting as an acid, and then if you notice back here in the other model, we see water acting as a base. What do we call that? We call that amphoterism. And amphoterism is the idea that a substance can act as either an acid or a base. Now, there's other amphoteric chemicals, but in the cases that we're looking at, we're just looking at water for the most part as our major amphoteric molecule. And because water has this ability to be amphoteric, it is very useful. And of course, then acids and base really rely on water because of it. So amphoteric is water, and so water can act as either an acid or a base, as we saw right here, acting as a base, and then we saw over here it's acting as an acid. All right, let's continue to just kind of look through a couple other examples to get this idea down. And I also want to bring forth the idea of conjugate acid-base pairs. So if we look in this equation right here, we have ammonia gas being bubbled through water, and if you bubble ammonia gas through water, it dissolves into ammonium ions, and then to do that, it takes a proton from the water, leaving hydroxide. So in this case right here, you see that this thing is acting as a base because it accepts a proton, and then the water here is acting as an acid. Now, notice that this is an equilibrium expression. So notice that what we're saying by this is that it can flow both ways. So if you're flowing this way, this acts as a base, and this acts as an acid. But look at when you flow back. When I flow back, the ammonium is going to actually donate a proton. So when you donate a proton, you're an acid. And then the hydroxide ion is going to accept a proton, and that makes you a base. And so we have the idea of conjugate pairs. And so a conjugate pair is simply the idea where you have two substances in a solution who simply differ by a hydrogen ion. So a conjugate pair is the other half or the other partner that differs by a hydrogen ion. So look at ammonia here and the ammonium ion. They differ by a hydrogen ion. So they're conjugate pairs, conjugate acid-base pairs. Acid-base pairs. And then similarly, the water is going to be an acid over here and a base over here, so it has its own conjugate acid-base pair. Let's look at a couple other examples down here. Here we have hydrofluoric acid, and so hydrofluoric acid is not a strong acid, and I'm going to illustrate a strong acid down here because it's a bit different. So hydrofluoric acid is going to go into water, and notice the fluorine loses a hydrogen, so this is clearly a hydrogen donor, making this an acid. And the hydrogen ion right here is going to be accepted by the water, so that makes it a base because it's a hydrogen ion acceptor. And then our conjugates are over here. When we flow back this way, the fluorine is going to pick a hydrogen back up, causing it to be a hydrogen acceptor, causing it to then become a base. And the hydronium ion is going to get rid of a hydrogen. It's going to be a donor, causing it to be an acid. So there's our conjugate pairs within that. Now, if we look down here, what's different about this than all these other examples? Well, this right here, if we're referring back to the last video, is a strong acid. And one of the things that we remember about strong acids is that they completely dissociate. And not only do they completely dissociate, their anion or cation, and I guess in the case of acids, the anion that they're with is neutral, completely neutral, which means that it will never interact with or take a hydrogen back, you see. So notice right here, we don't have an equilibrium expression. So in the case of strong acids, you don't have a conjugate acid-base pair with the acid. So there's no such thing as a conjugate acid-base pair if you're dealing with strong acids. So if we look at HCl, here's the acid, and this over here is nothing. It's just an ion in solution because it's not going to flow back. It's not going to take that hydrogen. And the water, of course, it is, of course, its own conjugate pair. So look for the strong acids in solutions when you're talking about conjugate acid-base pairs. If it's one of those strong acids, the reaction is simply not reversible because this completely dissociates. That's what defines a strong acid, and so these will not be conjugate acid-base pairs. Hopefully that explains everything well enough for you so that you are ready to answer any questions on amphoterism, acid-base pairs, strong, weak acid.